Welcome to Explore Learning STEM case on electrons and chemical reactions. This case study has two versions, a general chemistry version, which takes approximately 50 minutes to complete, and an AP chemistry version, which takes approximately 70 minutes to complete. In this case, students play the role of a forensic scientist working for the Secret Service. They begin by reviewing evidence discovered by the FBI while investigating a case of counterfeit coins. Before students start their investigation, they first review the background information needed to solve the case by entering the embedded handbook. This includes atomic structure, cations and anions, chemical bonds, covalent bonds, ionic bonds, electron shells, valence electrons, oxidation, reduction, redox reactions, oxidation states, metal plating reactions, and the activity series. More topics are covered in the AP version. All of the cases include questions for students, and teachers can follow their progress in real time using the heat map tool in their Explore Learning account. Every case also includes a scientific glossary to help with new terminology that is grade appropriate. After completing the handbook, students return to the case to analyze the evidence and form a hypothesis. They then test their hypothesis with a series of experiments to replicate the methods used by the subjects to make the counterfeit coins. Finally, students complete a case summary to communicate their findings and help develop their scientific writing skills. By engaging with a real-world case, students learn science by acting like scientists. Learn more at explorelearning.com.
Group 1 metals are very reactive because they have low ionization energies. One of the ways that indicates its high reactivity is the way that we store the metals. Group 1 metals are typically stored under kerosene or mineral oil to prevent or limit the reaction with the oxygen in the air. Let's look at some of the physical properties for Group 1 metals. We'll start out with lithium. The lithium is coated at this point in time with a layer of both the oxide and the nitride, and we end up with a fairly dull gray appearance. Group 1 metals tend to be relatively soft, and we can easily cut the metal with a knife. What we can do is we can see the shiny metallic surface underneath. If we bring in a conductivity tester, we can see that the lithium is an excellent conductor of electricity. If we add a piece of lithium to the water, one of the things that we notice is the fact that the lithium floats. Group 1 metals are less dense than water. We also see that the lithium reacts very rapidly with the water. This is a single displacement reaction producing hydrogen gas and lithium hydroxide. The lithium hydroxide is very water soluble and dissolves in the water. The hydrogen gas escapes. If we trap some of the gas in a test tube, we can test that the gas is actually hydrogen by testing its flammability. We can test that lithium hydroxide has been produced by adding an acid-base indicator. If we add some phenolphthalein, phenolphthalein is colorless in acid and red-purple in base, we can tell that the solution is basic due to the formation of the lithium hydroxide. We'll go down the column on the periodic table in Group 1 and look at sodium. Like the lithium, the sodium is stored in mineral oil to minimize reaction with the oxygen in the air. If we remove a piece of sodium metal, we notice that it's also coated over with an oxide coating. Group 1 metals become softer as you go down the column. The sodium is much easier to cut than the lithium. As we cut off the oxide layer, we can see the shiny metal underneath. It coats over very rapidly with a layer of oxide. The sodium is a metal and is an excellent conductor of electricity. If we take a piece of the sodium metal and add it to water, we notice a much more rapid reaction with the water. Like lithium, the sodium is less dense than water and floats. The metal moves across the surface, being pushed by the hydrogen gas that is produced. As you go down the column with Group 1 metals, the melting point of the metal decreases. The reaction is very exothermic, which causes the sodium metal to melt. The metal contracts into a very compact spherical form. We can again test that hydrogen gas is being produced by this single displacement reaction by trapping the gas and testing its flammability. We can test for the fact that we produce sodium hydroxide by adding phenolphthalein. The phenolphthalein turns a purple-red color due to the presence of the hydroxide ions, indicating the formation of the sodium hydroxide. If we continue down the column to potassium, we see that the potassium metal is also stored under mineral oil to minimize its reaction with the oxygen in the air. If we remove a piece of potassium metal, we can see that the potassium is coated over with a gray coating of the oxide. As we continue down the column, group 1 metals get softer and softer. The potassium cuts very easily. As we cut through the metal, we expose the shiny metal surface underneath. The potassium is extremely soft. We can easily flatten out the potassium metal. It has a consistency of cream cheese. The potassium is a metal and is an excellent conductor of electricity. If we add a piece of potassium metal to water, we see that it reacts much more rapidly with the water than the sodium. As you go down the column, the ionization energy decreases and the metal reactivity increases. The reaction is very exothermic, and the hydrogen that's produced ignites. We can test for the formation of potassium hydroxide by adding phenolphthalein. The solution turns red-purple due to the formation of potassium hydroxide.
How to balance chemical equations in 5 easy steps. Step 1. Count the atoms on each side of the equation. Let's count each type of atom. Sulfur, I have 8. Oxygen, I have 2. On the product side, sulfur, I have 1. And oxygen, I have 2. Note that if there's nothing after an element, we assume that to be 1. And that's it. We're done with the first step. Smooth. The big rule for balancing equations is that we can only change the coefficients. Those are the numbers in front of the atoms. The numbers after the atoms, the subscripts, cannot be changed. So let's balance this equation by changing the coefficients. If there's no coefficient written, we assume that it's 1. So right now there's a 1 in front of each of these terms. We can see that we have 2 oxygens on each side of the equation. So the oxygens are fine. But the sulfur atoms, we have 8 on the left side, the reactants, and only 1 on the right. Well, to fix that, I can change the coefficient in front of the sulfur on the right and make that an 8. So if I put an 8 here, that means 8 times the 1 sulfur, that'll give me 8 sulfurs. And now my sulfurs on both sides are 8, but this 8 here is also times the 2 oxygens. And that gives me 16 oxygens. So I've fixed the sulfurs, but the oxygens aren't balanced. I can change the coefficient here, though, to 8, because 8 times 2 equals 16. So now I have 8 sulfurs on each side, and I have 16 oxygens on each side of the equation. This equation is balanced. Step 3, so you don't forget, only change the coefficients. Let's try another problem. So in this equation, we have 2 hydrogens, 2 oxygens, over here 2 hydrogens, and 1 oxygen. How about, let's see, I'll put a 2 right here. So 2 times 2, that gives me 4 hydrogens, but 2 times the 1, that'll give me 2 oxygens. So my oxygens are balanced now, but my hydrogens are messed up. What I can do over here is put a 2 in front of hydrogen, and now 2 times 2, that'll give me 4. And now the atoms on each side of the equation are the same. This equation's balanced. Sometimes we'll have equations that look downright scary. Yikes. But if we have a polyatomic ion on both sides, like the SO4 or the NO3, then we can consider that ion to be just one thing. Let's see how that works. So here's the equation, and I've done my accounting below. You can see I have 1 calcium here, 1 calcium over here, and then I wrote the entire SO4 as one thing. And I have 1 of those here And over here I have one SO4, NAs, 1, 2 NAs on this side, and over here one NO3, and I have one NO3, but that 2 on the outside means I have 2 of them. So I have 2 NO3s. So if I put the coefficient of 2 right here, that means I'll have 1 times 2, 2 NAs, but this 2 also multiplies across, so 1 times 2 for the NO3s, that gives me 2, and now everything is balanced. So by treating those polyatomic ions as just one thing, it makes it a pretty simple equation to balance. Let's wrap up with one that sometimes gives people problems. So we can see we have 1 carbon, 4 hydrogens, and 2 oxygens. Easy. Over here we have 1 carbon, and then we have 2 oxygens, and then we have 2 hydrogens. But be careful. We have to count this oxygen over here as well. So we have 2 plus 1. That'll give us 3 total oxygens. I'll start by balancing the hydrogens. If I put a 2 in front of this hydrogen, 2 times 2, that'll give me 4. And that'll fix the hydrogens. But now I have 2 oxygens plus 2 times 1, 2 oxygens. That gives me a total of 4 oxygens. But that's good, because now if I put a 2 right here and change this coefficient, 2 times 2 equals 4, and now everything is balanced. This video has given you the basics for balancing equations, but you've got to practice to gain speed and expertise. The more you practice, the easier.
Hello everyone, today I'll tell you about such an element as neon. Neon is a noble gas that is located in the 8th group of the periodic table of chemical elements. Below helium, this gas is called noble because of the fact that it practically doesn't react with any substances, which means it does not give or attach electrons. Neon is a colorless gas with no taste or smell, the content of which in the atmosphere is 126 ppm percent by mass. Since neon has no chemical compounds, let's talk about its physical properties. By passing high voltage through the gas, it begins to glow with a red-orange light. The luminescence intensity will depend on the voltage and the gas pressure. The gas pressure in this vial is about 100 of the atmospheric pressure. This is done in order to reduce the voltage required for the elimination of the gas in discharge current. I'm not good in physics, but I will try to explain the mechanism of the luminescence of neon in simple words. As a high voltage source, I used an old plasma lamp, which has a generator of high voltage, high frequency and low amperage. At high voltage, electrons are seeking to fly out from the electrode, i.e. the cathode. When being approached by a neon vial, electrons fly out of the metal wire. Part of them passes through the glass and begins to encounter molecules of neon inside the vial. The neon atoms are excited by the collision with electrons. In the same way, as a man who has pushed in a roadway in a crowd. The electrons in the atom of neon are not inclined to wander around. Therefore, after the excitation, the atom relaxes and the electron goes back to its place. As a result, the atom emits a photon of light. The energy of the photons lies in the red part of the spectrum of visible light. My hand here plays the role of capacitor because of the current for the lighting of the neon in the lamp, because the current for the lighting of the neon in the lamp is extremely small. Based on this property is how many of the neon signs work, which are, by the way, filled not only with neon but also with other gases as well. The properties of the neon to emit light under the influence of electricity is used in Nixie tubes, like in these retro clocks, based on the Soviet indicators. The pressure of gas in these lamps is a few millimeters of mercury, and the current passing through the diges is about 100 volts. Due to the fact that the voltage is not very large, only a thin layer of gas near the diges glows, and not the whole lamp. This effect is called the glow discharge. The light emanates from the negatively charged electrode, the cathode. The color of the glow depends on the gas type. On a glow discharge, the gas conducts electricity well, which therefore means a strong ionization is always constantly supported within the gas. In these discharged lamps, a bit of mercury is added to the neon to facilitate an easier ignition of the gas and to increase the
Relationship between mass and inertia. We can study the relationship between mass and inertia by conducting the following experiment. Firstly, tightly clamp the hacksaw blade horizontally onto the table leg using the G-clamp. Stick a bit of plasticine with a mass of 30 grams onto the end of the hacksaw blade. Then, slightly pull the end of the hacksaw blade with the plasticine and release it so that it oscillates horizontally. Take the time for 10 complete oscillations using a stopwatch and record it in a table. Repeat the same step by using plasticine with a mass of 40 grams attached onto the end of the hacksaw blade and record the result in a table. Then, repeat the same step by using plasticine with a mass of 50 grams attached onto the end of the hacksaw blade and record the result in a table. Then, repeat the same step by using plasticine with a mass of 60 grams attached onto the end of the hacksaw blade and record the result in a table. Lastly, repeat the same step by using plasticine with a mass of 70 grams attached onto the end of the hacksaw blade and record the result in a table. From this experiment, we can conclude that the larger the mass of an object, the larger the inertia of the object.